Boys and girls, this is Mr. Manise here again with another super awesome video. And in this video, I'm going to walk you guys through day 2 of our probability packet. So I know I said that you guys weren't going to have to print out anything else for the unit, and you don't have to, but I would strongly encourage you guys to print out the 2 graphic organizers that I have posted to Google Classroom. In this lesson, we're going to talk about compound probability. So we're going to be looking at probabilities with coins, dice, cards, spinners, that kind of thing. So I would encourage you to print out 2 things, or you don't have to print them out. You can look at them on your computer screen if you want to. The first one that I've posted is it's kind of a snapshot of what's in a deck of cards, because we're going to be doing some problems where it's going to say something like, what's the probability of pulling a queen out of a deck of cards and pulling a black card out of the deck of cards or something. And I realize that unfortunately I get depressed every year in 2020 how many students don't know what's in a deck of cards or have never played cards. I know technology and the devices have kind of taken us by storm in the past decade or so. But I played cards my whole life growing up. It's a great pastime. I mean, we played on buses for hours, on church trips, and all that kind of good stuff. But anyway, let's just kind of talk through this real quick. What is in a deck of cards? You got 52 cards. You have 4 different suits. You've got clubs, diamonds, hearts, and spades. Half of them are red and half of them are black. And then you have each of these numbers. You got the ace and then all the way up to 10. And you got these 3 cards, jack, queen, king. And every suit has 4 of each of these guys. So there are 4 sixes, 4 tens, 4 queens, 4 aces, etc. Every year I have students that will ask me, Mr. Manise, what does it mean when it says face card? And I say, well, it's a card that has a face on it. All right, so that's what a face card is. All right, so an ace is not a face card. It does not have a face. Okay, you have numbered cards, that would be 2 through 10. You have letter cards, ace, jack, queen, king, A, J, Q, K. Those are your letter cards. Okay, so I will allow you guys to have access to this on the day of the quiz and the test, so you don't have to worry about memorizing these. But I would encourage you guys to especially, again, we're in April of 2020, right in the middle of the coronavirus pandemic. So I would encourage you guys to put the cell phones away in your free time and get out a deck of cards, go to Walmart and buy one, Google some fun games to play with your brothers, your friends, and your parents. If you're quarantined in your house, it's a great way to spend some time with the family. But anyway, that's what's in a deck of cards. So have this out to your side. What I posted online is actually has 2 of these, so I can cut them in half and make my copies, but you only need to print out the top half, of course. The other thing I would encourage you to print out is a graphic organizer, and both of these are under graphic organizers on Google Classroom. This is a graphic organizer that I put together years ago, this specifically for this lesson, compound probability. Okay, guys, maybe more so than any other unit in the geometry curriculum, this unit is so very important and is founded on what I call these trigger words. There's just 1 or 2 words in the problem that will tell you exactly what to do, how to solve the problem. The math in this unit and the math in this lesson is silly easy. I can teach my 5th grade daughter how to do the math. It's just multiplying and adding fractions, but it's historically, this has been a very tricky lesson because there's so many different types of problems. Now I'm going to go ahead and give you a 30,000 foot overview of this lesson, and of course I'll get into the nuts and bolts here in a minute when I start getting to the lesson. But basically I've broken this graphic organizer down into 2 planets, 2 universes. We've got planet and we have planet or. And these are going to be the 2 most important words of the whole lesson. When you see the word and, we're going to be doing stuff over here. When I see the word or, I'm going to be doing stuff over here. And within these 2 planets, we have different paths that we can take. And at the end of the day, it'll tell us at the bottom, this is what we're supposed to do when these criteria are met. I'll either be multiplying my probabilities or maybe I'll be adding my probabilities together to get the final answer. Okay, so I'm going to refer to this graphic organizer probably 20 times in this lesson, so I'd encourage you to have this out by your side as we go through this. Okay, so let's go ahead and jump into the lesson, compound probability. 2 things are happening, right? So in day 1, we talked about just basic probability. That could be the weather. What is the chance? What are the chances that it's going to rain tomorrow? Okay, that's just one thing that we're talking about. Compound probability is when I throw something else in there. I say, okay, what are the chances it's going to rain tomorrow and that the temperature is going to be above 80 degrees? Okay, now I got two different things going on, so we got to tackle that guy a little bit differently than basic probability. So the first thing that we have up to bat underneath compound probability are our independent events. Okay, so once again, this is my first referral. If I see the word and we'll see this in just a minute, I could be going down this path of independent events. Okay, now under planet and, okay, under this planet, two things, more than one thing, two different events are going to be occurring. How many? Two. Okay, all right, so I've got two different things going on. Okay, so it says independent events. It says event A occurring does not, absolutely does not affect the probability of event B occurring. Okay, so that would be like asking, what is the probability that Mr. Manise is going to play piano today and is going to eat chicken for dinner? Okay, those two things have absolutely nothing to do with each other. Whether or not I play piano in the morning has nothing to do with whether or not my family's going to eat chicken for dinner. Okay, those would be independent events. Okay, so how do I actually do the math? The probability of A and B, so this would kind of be like our union from the Venn diagrams. In this case, it would actually be the intersection because this is the overlap. The probability A and B. I'm simply going to multiply the probabilities. Okay, so that's all you need to remember. If I have independent events, I'm going to multiply these probabilities together. The probability of A times the probability of B. So let's check it out. All right, example number one says a coin is tossed and a six-sided number cube is rolled. Find the probability of landing on the head side of the coin and, okay, guys, please underline and highlight these trigger words. I'm zoomed out a little bit in this lesson today. Hopefully that'll help with the focusing issue. But also I'm going to be showing a bunch of stuff under the camera, so I need to give myself room to visually illustrate these concepts. What is the probability of landing on heads and rolling a 3 on the number cube? Okay, so here we go. I've got a coin and I've got a die. One die, two dice, three dice. Okay. I've got two different things that are happening, guys. Two things. I'm going to flip a coin. That's one thing. And I'm going to do something else. I'm going to roll this die. Okay. Two things are happening. All right. So find the probability of landing on heads and rolling a 3. Okay. So I want you guys to go back up here before we actually do the math. I want you guys to go back up here in this little part in the box, and I want you to write this out. I want you to write usually, not every time, usually we are going to see the word and replace. Usually, not every time. These are going to be our trigger words for the independent path under planet and. Okay, so what's the trigger word we saw in this problem? We saw the word and. Okay, now let's stop for a minute. Are these independent events? Does one thing affect the other? If I flip this coin, does that have anything to do with what I get on the die? No, they're completely independent. They do not affect each other. Okay, so I'm going to multiply the probabilities. So the probability of it landing on heads, of course, is 50%, or 1/2. The probability that I roll a 3 on this die, there's 6 different possibilities, so that's probability of rolling a 3 is simply going to be 1 out of 6. What do I do with those probabilities? I multiply them. 1/2 times 1/6 is 1/12. Okay, so only 1 out of 12 times when I do this experiment, only 1 out of 12 times, theoretically, okay, theoretically, will I get a heads and a 3. So let's see if this happens. Let's see if Mr. Manise can do it. Let's see if I can do it. I need a tails. No, I need heads. I need heads. Okay, I got my heads. And then let's roll a 3. Oh, okay. That didn't happen. Right, let me try one more time. Only 1 out of 12 chance it's going to happen. Now there's tails. Now that didn't happen. So it's not going to happen very often. Okay, 1 out of 12 times. Okay, example number 2. Here we go, our deck of cards. A card is chosen at random from a deck of 52 cards. It is then what? It is replaced. Okay, there's that other word. replaced. This tells me I'm in and land and I'm on the independent track. It is then replaced and a second card is chosen. What is the probability of choosing a jack? Bam. And an 8. Okay, so let me go back and refer to the graphic organizer once again. Okay, so I see the word and, we're on planet and then we're still on this independent track. Okay, now here is where I see with replacement. You're not going to see it every time. We didn't see it on the first one with a coin and a die. There's nothing to replace, okay, because we've got two totally different things. But now I'm talking about a bag of marbles or a deck of cards. I'm going to take the card out of the deck and I'm going to put it back. I'm going to pull the marble out of the bag and I'm going to put it back. Okay, and then what this says here, it says the denominator does not change, but we're going to multiply the probabilities. Okay, so what does that mean? Well, we're talking about a deck of cards. I want the probability of choosing a jack and an 8, but I'm going to put it back. So as we said before, I've got 52 cards in a deck of cards. I want the probability that I choose the jack, okay, and then I'm going to put it back. That's one event. I'm going to put it back, and now there is a second event. I'm going to draw a second card. That's two different actions. And I want to see what is the probability of getting a jack the first time and then an 8 on the second time. Okay, so we got to figure out what is the probability of getting a jack. Okay, so once again, if you're not familiar with a deck of cards, okay, let's pull this back up. Of course, I've got all this stuff memorized, but some of you guys may not. How many jacks are in the deck? Well, remember, there's one of each of these cards in every suit, and there's 4 suits. Every suit has 13 cards. 1, 2, 3, 10, 11, 12, 13. 13, 13, 13, 13. There's your 52 cards. I have 1, 2, 3. I have 4 jacks out of 52 cards. So the probability of choosing a jack on that first draw is 4 out of 52. Or, of course, yes, that's 1 out of 13. You do not need to simplify this fraction right now. You can simplify it at the end if you'd like. So the probability of pulling a jack is 4 out of 52. All right, and then I put the card back. So the second time that I draw, the probability of choosing an 8, that's the same thing, right? I still have 4 8s. That is also going to be 4 out of 52. Now, why does the denominator not change? Because I started off with 52 cards. I pull one card. When I put it back, I still have 52 cards. So that's why I say in the graphic organizer, when the two things are independent, they don't have anything to do with each other, the denominator does not change. Whether or not I pull a jack on the first draw has nothing to do with whether or not I'm going to pull an 8 on the second draw. Okay, so what do I do with the probabilities? I'm going to multiply them. Okay, so I'm going to multiply 4 out of 52 times 4 out of 52. Guys, please, please, please let your calculator do the work here. Okay, let your calculator simplify all your fractions. So I'm just going to do 4 over 52 times 4 over 52. I'm going to get that decimal. Okay, you could move the decimal 2 spots to the right, and that would be about 6%. Or to leave it as a fraction, I'm going to press math, just to refresh your memory on the graphing calculator. I'm going to press math, and that first option is frac, so I'll press enter twice. 1, 2, and that comes out to be 1 out of 169. Okay, which makes sense, right? Because 4 out of 52 is 1/13. 1/13 squared is 1 out of 169. 1 out of 169 times. Again, ask yourself, does my answer make sense? That means almost 1 out of 200 times. Okay, does that sound reasonable? Does that sound realistic? Well, the chance of drawing a jack is not very high. It's only 1 out of 13. And then I got to do another 1 out of 13. So that's not very likely. Let's see if Mr. Manise can do some magic here. I'm so disappointed that I don't get to teach you guys this unit in class. I get to show you all my card tricks in between classes and all that good stuff. You guys want to see a card trick? Check this out. This is the one-handed cut, so I'm only using one hand. I cut the deck with one hand. Pretty cool, huh? You want to see that again? Yes, you do. One-handed cut. Bam. Pretty cool. Okay, so it's not very. Let's see if Mr. Manise can pull the unimaginable. 1 out of 169 times, I'm going to get a jack and an 8. Okay, can I get a jack? Where's the jack? There's the jack right there. I feel it. Oh, so close. Okay. Let's keep going. Let's keep going. Example number 3. Okay, here's our marble in the bag trick. A jar contains 3 red, 5 green, 2 blue, and 6 yellow marbles. Okay, now, remember back up here when I said usually? That doesn't mean every time. I want you guys to cross out this and, okay? This is not the and that we're talking about. I literally want you to write in your notes, I want you to write, not the and we are talking about. That is just a good old-fashioned coincidental and. Okay, students love to make that mistake. Oh, I saw the word and. Oh, I'm going to plan an and. I'm going to be multiplying my probabilities. That's incidental. That's just saying I've got some marbles. I got 3 green, 2 blue, and 4 red, or whatever. Okay, and then it goes on to say a marble is chosen at random from the jar after what? After replacing it, a second marble is drawn. So 2 different events are happening. What is the probability of choosing a green? Boom, there it is. There's the and that we want. What is the probability of choosing a green and a yellow marble? Okay, so I don't have a jar of marbles, but what I do have is a little bowl of candied dog bones left over by the infamous Easter Bunny. And so basically we're going to be drawing a marble out of the bag, or I'm going to be drawing a dog bone out of the bowl, and then I'm going to be putting it back, right? So let's say there's 10 of each color, 10 blue, 10 red, 10 yellow. So I've got 30 total dog bones. So I want the probability of picking a red, putting it back, and picking a yellow. So when I put it back, I've got 30 dog bones to choose from. When I put it back on the second draw, I still have 30 dog bones to choose from. So again, the denominator does not change. Okay, I'm about to eat every single one of those after this video. Okay, so what is the probability of choosing a green marble? Okay, well, how many greens do I have? I have probability of green. I have 5 green out of a total of 8, 10, 16. 16 total marbles. And the probability of, what else they want? They want yellow. Probability of yellow, I got 6 yellow out of 16. Okay, notice the denominator does not change. Denominator does not change because we are putting it back. We're replacing it. I'm going to still multiply my probabilities. 5 over 16 times 6 over 16. Again, let's use our trusty calculator. Okay, we get that. Math. Fraction, I get 15 over 128. You must simplify your fractions, just like we talked about in the previous video. Always in math, simplify your fractions. Okay, number 4. A little bit tricky. If you guys want to try this one, you can pause the video and see what you come up with. So number 4 says a school survey found that 9 out of 10 students like pizza, as you would imagine. If 3 students are chosen at random with replacement, so I'm going to go to the cafeteria and I'm going to pick up 3 different students. I'm going to take one out of the cafeteria, ask them a question, send them back. Take another student out, send them back. What is the probability that all 3 students like pizza? What is the probability that all 3 students like pizza? Do you see the word and? Do you see the word or? No, I do not see either of those words in the question. Okay, so what do? It's implied. It's in there. Okay, if I see the word replacement, I know I'm in independent land. Okay, but the and is implied. I'm going to survey one student, put them back, and survey another student, put them back, and survey a third student. Okay, so most of the time I've been holding up the 2. I've got 2 different events. This time I got 3 events. Okay, it's just 2 or more. 3 different things are happening. Okay, all right, so what is the probability that the first student, I'm just going to put a check for the first student likes pizza. The first student liking pizza is 9 out of 10. Okay, I'm going to put that student back in the cafeteria and poll another student. What is the probability that the second student likes pizza? Nothing changed. It's still 9 out of 10. What is the probability that the third likes pizza? 9 out of 10. So the chances of me drawing back to back to back students who like pizza is like, what is the probability of flipping a coin and getting tails, tails, and tails? Okay, so I'm simply going to multiply these probabilities together. 9 out of 10 cubed, or 9 out of 10 multiplied 3 times. I'll do that. I'll cube it. Parentheses 9 divided by 10. I'm going to raise that to the 3rd power. and I get 0.729, which is 729 out of 1,000. Or again, in this case, you could say 72.9%. Okay. And you might say, that's a little bit lower than maybe I would have thought, because, I mean, chances of getting 3 students in a row who like pizzas seems like it would be very high if 90% of the people like pizzas. But every time you keep going, every time you ask a third person, a fourth person, a fifth person, eventually you are going to pick somebody who actually doesn't like pizza. Okay, so this percentage is not as high as you might have thought. It's only 73. About 3 out of 4 times you will get back-to-back students who like pizza, and then you find that one student who doesn't like pizza, and we send that student to ISS immediately because he doesn't like pizza. Okay, that is the independent track. Okay, that's Planet and going down this independent track. Independent, they don't have anything to do with each other. I'm putting stuff back. The denominator does not change. We multiply the probabilities. Okay, now we're going to talk about dependent events. Okay, so we're still under the umbrella of Planet and, but now I'm going to talk about dependent events. Okay, so it says event A occurring absolutely affects the probability of B occurring. Okay, so in that case, is the probability of A intersection B. I'm still going to multiply the probabilities. Okay, that doesn't change, but it's the probability of A is the probability of B based on the probability of A. That doesn't really matter so much. What you really need to remember is that usually we're going to see the words with replacement. And I also want you to write usually see the word and. I'm still in Planet and. But this time, instead of putting the marble back in the bag, putting the card back in the deck, we're going to keep it out. Okay, so what do you think happens to the denominator? Okay, all right, dependent events, we're going to see without replacement. Now the denominator does change because I don't have 52 cards in the deck. If I pull a card out and keep it out, now I only have 51 cards in the deck. If I have a bowl of 30 dog bones and I pull one out and I leave it out, then I don't have 30 anymore. I only have 29 left in the bowl. Okay, so the denominator is going to change. But I still, at the end of the day, I'm still going to multiply my probabilities. So example number 1, a jar contains 3 red, 5 green, 2 blue, and, okay, put an X through that. That's not the and we're talking about. A marble is chosen at random from the jar, and then a second marble is chosen. So 2 things are happening without replacing the first, without replacing. What is the probability of choosing a green and a yellow marble? Okay, Planet and. Okay, so now what are the chances of drawing a green marble? Probability of green is still going to be, it's the same exact problem. We still have 5 green out of 16 marbles, okay? And then the probability of choosing a yellow is going to be, when I choose a yellow, it's going to be 6. But now there's not 16 marbles in the bag anymore because I don't replace it. I keep one of those out. So now you notice my denominator changes. It drops by 1. So instead of 16 marbles, now I only have 15 marbles. But I'm still going to multiply those probabilities. 5 out of 16 times 6 out of 15. Okay. Now, would you anticipate, back up here, we got 15 out of 128. Would you anticipate this number being more or less than that since this denominator changes? What do you think? Is it going to be a higher probability or a lower probability? Well, let's punch it in and see what we get. 5 out of 16 times 6 out of 15. That comes out to be 0.125. This one up here came out to be, I think, 0.11. So this one is a little bit higher because our denominator is a little bit smaller. So again, math fraction, that's 1 out of 8. So 1 out of 8 times I will draw a green, keep it out, and then draw a yellow. Okay, so 1 out of 8 is correct. All right, number 2, an aquarium contains 6 male goldfish and 4 female goldfish. That's an incidental and. That's not the and we're talking about. You randomly select 2 fish from the tank without replacing the first one. What is the probability that both fish are male? Do you see the word and in the question? I'm always talking about the question. Do you see the word and? Nope. Do you see the word or? Nope. Okay, so what do? The and is implied. Again, if you see the word replace without replace, if you see those words, okay, with or without replace, we're in planet and, whether you see that word and or not, okay, but the and is the important trigger word, okay, but it's implied. So what we're saying is, I want to pull a fish out of the tank, out of the aquarium, and I want a male. Both fish are male. I want a male, and then I'm going to pull a second fish, 2 events. I want a male and another male. Okay, so that and is implied in the problem. Okay, all right, so what is the probability that the first fish is a male? Okay, we got 6 male out of 6 plus 4. We got the probability that the first is a male is 6 out of 10. Okay, the probability that the second is a male, okay, second one is a male. Now, if I pull the first fish out of the tank and it is a male, okay, now I don't have, now this is a little tricky because now the numerator also changes, okay, because I don't have 6 fish in the tank anymore. I already got that male, okay. I'm assuming the probability of A, or excuse me, the probability of B based on the fact that we already got A. I want the probability that the second is male, assuming that the first one is a male. So now I only have 5 males left in the tank. And now how many total fish do I have in the tank? Remember, these are fish. Here's a male. The red is a male. I've taken a male and I've kept it out of the tank. Okay, so my numerator is now changed and my denominator is changed. Okay, I don't have 6 male, I only have 5 male, and my denominator I only have 9 total fish left. Okay, now again, I know I kind of took a long time to say that, but I know this concept historically has been very tricky for a lot of students, so I want to really slow down and make sure you guys have a good understanding of this. Pause and rewind the video if you need to hear it again. All right, I'm still going to multiply my probabilities. 6 out of 10 for the first male, 5 out of 9 for the second male. That comes out to be 1/3. Okay. All right. If y'all want to pause the videos, you can try number 3 on your own. Okay, number 3 says a random sample of parts coming off a machine is done by an inspector. He found that 5 out of 100 parts are bad on average. If he were to do a new sample, what is the probability that he picks a bad part and then picks another bad part if he does not replace the first? So this will be without replacement. Okay, so we're still in and land. So I see the word and, I'm going to multiply my probabilities every time. Okay, so by the way, if you got an assembly line and 5 out of 10 parts are bad, 5 out of 100 parts are bad, 5% are bad. By the way, in the real world, that don't cut it. Okay, I worked in the industry for 10 years, and 5% of the product being bad is not good enough. 1 out of 100 might be acceptable, but really should be more like 1 out of 1,000 or 1 out of 10,000 or something like that. If you're working for Coca-Cola, imagine if 5 cans of Coke that came off the assembly line were bad. That's not very good. Something's wrong with the machine. You need to engineer somebody to go figure out what the problem is and make it more efficient. Anyway, okay, so what is the probability that he picks a bad part and another bad part? That's 2 events. He's taking 2 different things off the assembly line. The probability that the first is bad, that's our 5 out of 100. Okay, now if we assume that the first one's bad, the probability that the second one is bad is what? I've already pulled 1 off, okay, so I don't have 5 bad parts anymore. Now I only have 4 bad parts, so my numerator does drop by 1, and the denominator, when I see does not replace, my denominator always drops. So now I only have 99 assembly parts to choose from. So I'm going to multiply those probabilities together, 5 over 100 times 4 over 99, and that comes out to be 1 over 495. Okay. Compound probability, independent, dependent. Okay. Let's keep going here. Next page. This is super easy. This is to simply determine whether or not events are independent or dependent. It says substitute substitute what you know into the formula. The probability of both is the probability of A times probability of B, and check to see if the equation holds true. So all we're doing, guys, is we're just multiplying numbers and seeing does the left side equal the right side. If they're equal, then it's independent. If they're not equal, it's not independent. Simple as that. Example 1, let M be taking a math class, S is taking a science class. M and S is taking a math class and a science class at the same time. Suppose that the probability of taking a math class is 60%. I don't know where they're getting these numbers from. That should be more like 90%. Suppose probability of taking a math class is 60% and the probability of taking a math class is 50% and the probability of taking both is 30%. Are these two probabilities independent? Do they have anything to do with each other? So I simply want to see, is the probability, this would be like probability of A and probability of B. Okay, I just want to see, is the probability of M times the probability of the science class, question mark, does that equal the probability, oh my gosh, why did I write an 8? S. Does that equal the probability of taking a math and a science class? Okay, probability of math is 60%, 0.6. Probability of science is 0.5. And the probability of both is 0.3. Put a little question mark. Is 0.6 times 0.5, you don't need a calculator for this, is half of 0.6, is that 0.3? Yes, it is. That equation holds true. So yes, these are independent. They have nothing to do with each other. Okay, think about real world. That makes sense, right? Doesn't, whether or not you have a science class has nothing to do with whether or not you have a math class, especially when you get to your senior year and you've got options. Okay, so example number 2. In a class, 60% of the students are female, 50% of all students in the class have long hair, 45% of the students are female and have long hair. Of the female students, 75% have long hair. Let F be the event that student is female. Let L be the event that the student has long hair. One student is picked at random. Are the events of being female and having long hair independent? Holy cow. Wow, that's a lot of stuff. I always tell my students in word problems, read the question 3 times, especially something like this. You probably read that and had no idea what it was talking about. Let's go read it again. In a class, 60% of the students are female. Okay, 6 out of 10 are female. 6 out of 10 are female. Half of the students have long hair. Half have long hair. Okay. 45 of the students are female and have long hair. Of the female students, 75% have long hair. Are the events of being female and having long hair independent? Okay. Are the events of being female? Okay, that's what we need first. So the probability of being female is what? 60%. Okay, got that. The probability of being female and having long hair. So what is the probability of long hair? Do we have that number? Yes, we do. Half of the class has long hair. Okay. All right. Are these two independent? So I need to see, is the probability of being female times the probability of having long hair, question mark, does that equal the probability of being female and having long hair? Okay, so the probability of female is 0.6 times probability of long hair is 0.5. Do we have the probability of being female and have long hair? Female and have long hair. That's 45%. Okay, so I just need to see, does 0.6 times 0.5, does that equal 0.45? We just did that. No, it doesn't. Okay, so I would say no, these are dependent. Now this is probably a tricky problem because guess what? See that guy right there? 75% have long hair. We never needed that. Never needed that at all. And guys, that's real world. You're going to have all kinds of problems in the real world where you have all kinds of information that you may or may not need. Okay. Okay, so that's it, guys, for and land. Okay. This video is already 34 minutes long, and we just got through and. This is a tough lesson, guys. Okay. So I apologize if this video goes over a little bit, but it's critical that I really slow down and explain this stuff step by step. Okay. Now, that takes care of and. Now, we have gotten into our spaceship, and we have left the building. Elvis has left the building, and now we're hopping over to a brand new universe, a brand new planet, the planet of Or. Okay, Or. And now I'm going to be looking at what happens when I'm exclusive and inclusive. On planet And, multiple things are happening. Most of the time, two things are happening. Sometimes more than two things are happening. On planet Or, guys, one thing is happening. One event. Over here, I'm drawing a card and I'm drawing another card. Over here, I'm drawing one card. One card. And I want to see if it's this or this. Okay? One event. All right, so let's check it out. Mutually exclusive events. Events that cannot happen at the same time are called mutually exclusive. What does the word exclusive mean? You can't come to the party, right? You're excluded. VIP, very important person. Only certain people can come to the party. Everybody else is excluded who doesn't meet the criteria. We're not good enough to be in the VIP room. Okay, it says if events A and B are mutually exclusive, if they cannot happen at the same time, then the probability of both A and B occurring is a big old fat 0. They cannot happen at the same time. That would be like rolling a die, okay? And I want to know, what is the probability of rolling a 3 or a 4? How can I be a 3 and a 4 at the same time? I can't. So the probability of rolling and it being a 3 and a 4 at the same time is 0. That's impossible. Okay. The probability that either A or B occurs is the sum. Okay, so when we are in the universe of Or, when we're on planet Or, we are going to add the probabilities. Okay, it's the sum of the probability of A occurring and the probability of B occurring. So we're simply going to add our probabilities together. Okay, planet And, multiply. Planet Or, we add. Okay, now that's mutually exclusive. Okay, so that's going down, we're on planet Or, that's going down this path. Okay, there's no overlap. These two things cannot happen at the same time. We're going to add the probabilities. Now we're going to look at inclusive. Events that have outcomes in common are inclusive or overlapping. That means they can happen at the same time. Okay, that would be like taking my die and saying, what are the chances that I roll a 3 or an odd number? Can I be a 3 and an odd number at the same time? Yes, I can. I could roll a 3 or I could roll an odd number. Two different things can happen at the same time. I can be a 3 and odd at the same time. That's inclusive. Okay, so it says the probability is still going to be the sum. I'm still going to add those guys together. It's the sum of probability A occurring and the probability of B occurring minus the probability that both A and B will occur. This is probably one of the hardest concepts in the entire probability packet. This guy right here. I'm going to add the probabilities together, and then I have to subtract out the intersection. Remember that word overlap. I must subtract out the overlap. Why do I have to do that? I want you to put this in your notes. The reason I have to subtract out the overlap is to account for double counting. Okay, I cannot count the same thing twice. I'm going to get into, I have a little illustration I'm going to do here in just a minute. Hopefully we'll make the light bulb go off and you'll go, oh, that's why I have to subtract out the overlap. So let's go ahead and jump in. Example number 1. The directions are saying tell whether or not it's exclusive or inclusive and then find a probability. So you have several coins in your pocket. We've got 5 dimes, 8 pennies, 2 nickels, and 3 quarters. Okay, here we go. Again, that is not, I'm going to write this again, not the and we're talking about. Okay, we are not on planet And. That's just an incidental and. If you reach in your pocket and pick out one at random, what is the probability of choosing a dime, boom, or a penny? A dime or a penny. Okay, so how many things happened? One thing happened. I'm not reaching in my pocket and pulling out a coin, putting it back, and drawing a second coin. I'm simply pulling one coin out of my pocket, and I want to see, is it a dime or a penny? Okay. Now, is this inclusive or exclusive? Can these two things happen at the same time, or is there some overlap? If I pull one coin, can I be a dime and a penny at the same time? Obviously not. Can't be two different coins at the same time. So if it can't happen at the same time, that is exclusive. Okay. What do I do with the probabilities? I add them together. So what is the probability of picking a dime out of my pocket? Let's see, I've got 5 dimes out of 13, 15, 18. 18 total coins. Okay, what is the probability of it being a penny? I have 8 pennies out of 18 coins. What do? I add them together. Multiplying fractions is easy. You just multiply across the top, multiply across the bottom. When you add fractions, you must have a common what? You must have a common denominator. If you do have a common denominator, just add your numerators. That would be 13 out of 18. If this was a denominator with 17 or something, please guys, just use your calculator. Add the fractions, press math, fraction. Let the calculator simplify the fraction for you. So we got 13 out of 18. Let me try that again. 13 out of 18. Does that make sense? Well, that's a big chunk, right? 13 out of 18. What is that as a decimal? 13 divided by 18. Okay, that's about 72%. That's almost 3 out of 4 times. Does that make sense? It should, right? Because we're pulling one coin out, and I just need it to be a dime or a penny. Well, that's the bulk of the coins that we're talking about. 13 of them are either a dime or a penny. Let's assume that you made a mistake. Let's assume that you made the classic mistake and you saw the word and you multiplied. You multiplied 5 over 18 times 8 over 18. Watch what happens. 5 over 18 times 8 over 18. I get 0.12. That's 12%, guys. 12%. You mean to tell me that only 1 out of 10 times I'm going to draw a dime or a penny when that's the bulk of the coins? Okay, so ask yourself, does my answer make sense? Does it sound reasonable? Okay. All right, so let's go to the next one here. If you randomly choose a card out of a standard 52 deck of playing cards, what is the probability of choosing a heart, bam, or a queen, or a queen? Okay, so looking at a deck of playing cards, okay, I need to see, I'm trying to figure out, can they happen at the same time? If they can't happen, it's exclusive. If they can happen at the same time, if I can be the same thing at the same time, then I've got some overlap. Can I be a heart and a queen at the same time? Well, of course. One of the best cards in the deck, right? Queen of Hearts. Yes, I can be a heart or a queen at the same time. Okay, so there is some overlap that I have to subtract out. So watch what happens. Check this out. Okay, so the probability, so this is going to be inclusive. I do have some overlap. I can be the same thing. I can be both of these at the same time. The probability of drawing a heart. Okay, again, if you need your little sheet here, get your sheet out. There are 4 suits. There are 13 hearts. So that's 13 out of 52. Basically 1/4 of the deck, right? That's the same thing as 1 out of 4. 13 out of 52. 1/4 of the deck is hearts. And what's the probability of being a queen? I have 4 queens, right? So 4 out of 52, or 1 out of 13. Excuse me, whoops, sorry. 4 out of 52. Okay, 13 out of 52 are hearts, and 4 out of 52 are queens. Okay, so when I see the word or, what do I do in my probabilities? When I see the word or, I'm always going to add my probabilities. But here, I've got to subtract out the overlap. So I'm going to add these together. I'm going to add 13 over 52 plus 4 over 52. Okay, now let's stop for a minute. Let's say that that's all we did. If we did not subtract out the overlap. If we did that, I don't know why I can't write tonight. 52. 13 out of 52 plus 4 out of 52. That would give me, I'm just going to write this over here, that would give me 17 out of 52. So we're saying there's a 17 out of 52 chance that I'm going to be a heart or a queen. Okay, so let's model this. 17 out of 52. All right, I'm going to get all of my hearts. Talk about that one. Let's get all the hearts, all the hearts. You want to see a card trick? Watch this. Now you see it? No, you don't. Okay. Hearts. Okay. So there are all of my hearts. Okay, 13 hearts. And now, so let's count these. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There are all of my hearts. Now let me go get the 4 queens. Okay, there's one of my queens. There's 2 of my queens. 3 of my queens. Wait, what? Where's my 4th queen? My 4th queen is over here, guys. Okay? That's why you have to subtract out the overlap. If I count these, I have 13 here, 13 hearts, but I only have 3 queens. That's why you must subtract out the overlap. I must subtract out how many cards are queens and hearts at the same time. I only have one of those. I only have 1 queen of hearts. So I have to subtract out that 1 out of 52. So now that gives me 17 minus 1. That gives me 16 out of 52, which actually reduces to 4 out of 13. Why did I have to do that? Because I can't double count. If I kept it as 17, that means I'm counting the queen of hearts here, and I'm counting the queen of hearts and the queens. I'm counting it at 2 different spots, but I only have one of these guys, or one of these ladies, I should say. Okay, so you either got to pick. Either you're going to include the queen on the queens, or you're going to include the queen on the hearts. One of the two. You can't put them in both places. That's why we have to subtract out the overlap. So if you want to put that in your notes, the queen of hearts is your overlap. Okay, by far one of the hardest concepts for students to get down in this unit. Okay, hopefully with this little illustration that kind of makes more sense to you. Okay, so let's keep it going. Let's keep it going. Okay, we're almost home. Okay, just a few more. Okay, example number 3, using the spinner below, what is the probability of spinning and landing on an odd number or an 8? Okay, so I'm on planet or. That means I'm adding my probabilities. Okay, an odd number. Okay, so looking at the spinner, what is the probability that we get an odd number? Okay, so I've got 1, 3, 5, 7, right? I've got 4 out of the 8 numbers, or 1/2, are odd, or the probability of getting an 8. So the probability of spinning an 8, there's only one of those. That's 1 out of 8. Okay, now, is this exclusive or inclusive? Can I be an odd number and an 8 at the same time? No, because odd is odd and 8 is even. So this is exclusive. So write that in your notes. Exclusive. They cannot happen at the same time. If they cannot happen at the same time, there is no overlap to subtract. You just simply add the probabilities. So I just add 4 out of 8 plus 1 out of 8, and that gives me 5 out of 8. Okay, no overlap. Okay, I want y'all to try, maybe y'all should pause the video and try number 4 and number 5 on your own. Okay, so hopefully you guys are able to get these. Using the spinner below, what's the probability of spinning and landing on an even number or, so I'm on planet or, and I'm going to add my probabilities, or a multiple of 4. Okay, so I need the probability of an even number. Okay, that's going to be half of those, right? 6 out of 12, half of those are even. What is the probability that I am a multiple of 4? Okay, well, 4, 8, and 12 are multiples of 4. I have 3 of those. Okay, so 3 out of the 12 numbers are multiples of 4. Okay, now, can I have any overlap? Can I be even and a multiple of 4 at the same time? Yes, I can. How many of those? I have 3 of those. The 4, the 8, and the 12 are all multiples of 4, but they're also even. So when I add these together, 6 out of 12 plus the 3 out of 12, This is going to be inclusive. So I must subtract the overlap. Okay, how many of these guys are both even and multiple of 4 at the same time? 3 of those. So I have to subtract out 3 out of 12. Well, guess what happens? Those just cancel. And I'm left with 6 out of 12, which is 1/2, 50%. Huh? Say what now? Why is this 50%? Well, let's think about it. If you're saying, I want to spin this, I'm going to get one number, I want it to be either a multiple of 4 or an even number. If I spin a multiple of 4, am I not also even at the same time? Yeah, so the multiple of 4 is insignificant. It's meaningless in this problem. Basically, what it's asking is, what are the chances of spinning and getting an even number? Because if you're a multiple of 4, you are even. So that's why the math checks out, and I end up with only 1/2. Okay. Number 5, hopefully you're able to get that. If you randomly choose a card out of a deck of 52 playing cards, what is the probability of choosing a spade or an even number? Okay, so I'm playing it or. This will be, well, actually, I'll put this back up after this problem. Okay, so I'm going to add my probabilities. Okay, can I be a spade and an even card at the same time? Okay, well, here are all of my spades. Okay, yes, I can be even and a spade at the same time. The 2 of spades, 4 of spades, 6 of spades, 8 of spades, 10 of spades. Those are our numbered cards. We don't include the face cards or the aces. These are numbered cards. Okay, even. I know some of you guys might think, well, queen is 12. No, we're not talking about that. We're talking about only the numerical cards. Okay, so the probability of it being a spade, how many spades do we have? That's a whole suit. So 1/4 of the deck is our spades. So I'm going to say 13, you could do 1 out of 4 or 13 out of 52. I'm going to keep the denominator out of 52. That way we have a common denominator when we add our fractions. It just makes it a little bit easier. But you certainly could just write down 1/4. Okay, what is the probability that I pull an even numbered card? Even. Okay, how many evens do we have? We have all of the 2s, all the 4s, all the 6s, all the 8s, all the 10s. And we have 4 of each of these guys. So 4, 8, 12, 16, 20. We have 20 even numbered cards out of the deck. Okay, so 20 out of 52 are even. Okay, so I'm going to add those together. 13 out of 52 plus 20 out of 52. And we already said, yes, I do have some overlap. So this is also going to be inclusive. We got to subtract out the overlap. How many of these guys are even and spade at the same time? We said that was 2, 4, 6, 8, 10 of spades. 1, 2, 3, 4, 5 cards are even and spade at the same time. So we must subtract out those 5 even spades so we do not double count them in the spades and the even numbered in the piles, I guess, if you want to think about it that way. So that is 33 minus 5, so that is 28 over 52. We always want to simplify our fractions. That comes out to be 7 out of 13. Whew. Tough lesson, guys. Tough lesson. Please make sure you do your homework. I'm going to recap real quick here. Recap, stay with me. One more time. Compound probability. If I have 2 or more events, if I see the word and, I'm going to plan it and. That means that I'm going to be multiplying my probabilities, and then it's just a matter of whether or not it's independent or dependent. Do I see the words replace or without replace? If I see replace, the denominator does not change. I'll multiply the probabilities. If I see the word and in the question, and I do see without replacement, then the denominator decreases by 1 every time. Now, the numerator might also decrease. We saw that with the fish in the aquarium. So sometimes the numerator decreases as well, but the denominator definitely decreases by 1 each time. But I'm still going to multiply the probabilities. When I'm on planet OR, I'm either exclusive or inclusive. If it's exclusive, they cannot happen. They're excluded from each other. They can't happen at the same time. So there's no overlap. I simply add the probabilities. If there is some overlap, they're inclusive, then I add the probabilities and subtract out the overlap. Okay. Whew. Okay. A lot of stuff there, guys. Hope you guys enjoyed this. Hope I was able to explain it in a way that you could understand. Got to do lots of these problems or practice. Hope you enjoyed it, and we'll see you on the next video.